Heat energy in chemical reactions. We're going to talk a little bit about how much heat is involved in chemical reactions, but it's more important to discuss if the heat is going into the chemical reaction, that is it being absorbed during the chemical reaction, or is it coming out of the chemical reaction? In other words, is heat being produced or released by the chemical reaction? So first we're going to talk a little bit about the laws of thermodynamics. Thermodynamics is the study of the heat and movement of heat in chemical and physical reactions. So the first law of thermodynamics states that the internal energy may be transferred as heat or work, but it cannot be created or destroyed. Well, what does that mean? Well, the internal energy is the amount of heat energy within any substance or group of substances or container of substances. And you can think of the energy as being related to the speed and vibration of all the particles within a certain container that you're looking at. And that average speed translates to a certain amount of kinetic energy or heat that can be observed with that object. So what this law is stating is that you can transfer heat into this, you can transfer heat out, you can do work onto the system, or you can let the system do work on other things, but the energy cannot be created or destroyed. In other words, you can convert one kind of energy, work, into heat, or chemical energy into heat energy, or any other energy into any other energy, but you can't destroy any energy. It has to go somewhere, and it has to come from somewhere. And this is the conservation of energy law. The second law of thermodynamics says that the total entropy, and entropy is an extremely complicated term, but one easy way to think about it is it's a measure of disorder. Not order, but disorder. So the more disordered molecules are, or particles are, or some substance is, that is a higher amount of entropy. So the entropy of the entire universe always increases with time. Now, does this mean that you never have parts of the universe where order is being increased? No, of course not. We build buildings. Those are more ordered than the construction materials that we start with. We synthesize more complex chemicals from simpler chemicals. That is going in the opposite order. We're making more order than disorder. But if you look at all of the ordering and disordering throughout the entire universe, the total amount of order is always decreasing. It's always increasing in disorder over time throughout the entire universe. We abbreviate entropy, or the change in entropy, as delta S. So this is saying that delta S always is changing in a positive way. It's always increasing all the time throughout the universe. And in fact, some physicists believe that this increase in entropy is responsible for time itself. The fact that time only goes in one direction because the total entropy is always increasing. It never decreases in time throughout the universe. The third law of thermodynamics says that at absolute zero, so what is absolute zero? Absolute zero is the lowest temperature possible. It's the temperature when you have removed all heat energy from a substance, all vibrational energy, all movement of the particles. And so at absolute zero, the entropy of a perfectly ordered crystalline substance, in other words, all the atoms are sitting in place, they're not moving, they're not vibrating. At that point, the entropy, the disorder, is zero. In other words, it's a perfectly ordered system. Now, I will tell you, there is no such thing as being able to actually get to exactly absolute zero. Theoretically, if you were to be able to get to absolute zero, then there would be no disorder and essentially no movement of any particles, not even vibration of atoms or any of the subatomic particles that we know atoms are composed of. Now, this is impossible to get to. Scientists have gotten within a billionth, I believe, or close to a billionth of a degree above absolute zero, but they never actually reached absolute zero. It is theoretically impossible to reach. Now, once all these laws were created years ago, they realized, oh, wait a minute, we need to define something else first. So they created what was called the zeroth law. And this says that if you have two thermodynamic systems, and you can just think of this as two substances or two collections of substances, are in thermal equilibrium with a third substance, then they are in thermal equilibrium with each other. Okay, what does that even mean? That, you can think of this as if two rooms have a room in between them, and the doors are open between them, allowing the temperature to freely flow between room A and B, but the doors are open between B and C, then A and C are also going to be at thermal equilibrium. And thermal equilibrium really just means they're all at the same temperature. They all have the same average kinetic energy. They all have the same average amount of heat per substance in those areas. So if you have two areas that are the same temperature because they can transfer heat back and forth very easily, with a third area, well then all three of them are in thermal equilibrium with one another. And this was actually used to create the concept of temperature, which it was later realized maybe we should define temperature and the movement of heat in order to allow for the first, second, and third law to be make any sense to actual physicists. All right, so there are two basic kinds of chemical reactions we're going to talk about. Exothermic and exothermic. The word exothermic literally means heat is going out. Thermic means heat. Exo means out. You can think of it as exiting. The thermic, the temperature, the heat is going out of a chemical reaction. And the other type is endothermic. You can think of it as heat is going into this chemical reaction. In other words, heat is being absorbed in the reaction. So an exothermic reaction, heat is released. And most reactions that you know about are exothermic. They generate heat. They get warmer. But there are some reactions that absorb heat. These are called endothermic reactions, heat going into the chemical reaction. Heat is absorbed. And the most famous of these, for your purposes, are these cold packs that you can buy in a drugstore, and you smack the bag, and two chemicals mix together, and suddenly it gets cold. Well, that's because heat is being absorbed. Well, where is it being absorbed from? Well, it's being absorbed from your arm or your shoulder or your knee or wherever you're putting that cold pack on. So in an exothermic reaction, heat is actually a product. You have reactants producing the products plus a heat product. So heat is an actual product in an exothermic reaction. Heat is going out. It's a product. Whereas in an endothermic reaction, you can think of as heat as a reactant. You are adding heat to your reactants that make them turn into products. So an exothermic reaction, because it produces heat, as I said, feels hot. And an endothermic reaction, because it's absorbing heat, feels cold. Now, if you study physics, you find out that to a physicist, there's no such thing as cold. There is heat, and there is the absence of heat. And we as humans perceive the absence of heat, or a low amount of heat, or a drop in the amount of heat, as feeling cold to us. But there's no actual thing called cold to a scientist. Heat is the thing, and you either have heat and it feels warm or hot, or you have lost heat and it feels cold or cool. So in the case of an exothermic reaction, where did this heat come from? Well, it's because the reactants you start with are higher energy. They have higher energy to start with, and when you make the products, that energy has to go somewhere. Well, it's released as heat. Whereas in an endothermic reaction, the reactants need energy. Look at the reaction written. A plus B plus heat produces C plus D. The reactants need energy to get up to a higher energy level products. These, in this case, the products are a higher energy, and in order to get to that higher energy, you need to pump in heat. And when you pump in heat, it means the heat is being taken away from the surrounding area, the surrounding environment, and that would make it feel cold to you if you touched it. So let's talk about these reactions one at a time. exothermic reaction. Heat is going out. And here's a very classic exothermic reaction. We're burning carbon with oxygen gas to produce CO2. This is both a combustion reaction because we're burning a carbon compound, though there's no water being produced, but it's more properly referred to as a combination reaction. We're combining elemental carbon with elemental oxygen gas to produce CO2, carbon dioxide. And this is a very exothermic reaction. It produces a lot of heat. Why does it produce a lot of heat? Well, because the heat energy of the reactants to start with is kind of high to begin with. They're not the most stable forms of substances. There are more stable substances like CO2. CO2 is extremely stable relative to oxygen gas and carbon. Carbon's pretty stable, but oxygen gas is not really that stable. The bonds that hold oxygen together are not particularly strong, but the bonds that hold CO2 together are very strong, so they're lower energy, they're more stable. And when you go from one to the other, of course, I've shown in green this transition state, this activation energy you have to get through first. That's because you're breaking bonds to get there. But let's just consider the blue lines. We're going from a high energy pair of reactants to lower energy products, and as a result, heat is released. You are dropping in energy between your reactants and products, and that energy has to go somewhere, and that is because the products are more stable. So heat is an actual product in this reaction. If I reacted 1 mole of carbon, that's about 12 grams, with 1 mole of oxygen gas, that's about 32 grams, I'll produce 1 mole of carbon dioxide gas, that's about 44 grams, plus 395,000 joules, 395 kilojoules. This is a lot of energy. This is why we burn things like coal. Coal is mostly pure carbon, and we burn carbon to make heat energy. Unfortunately, we also make CO2, which does a lot of terrible things to warm our environment. This is one of the major reasons why we have global climate warming. So we're trying to avoid doing this, but burning carbon fuels will produce enormous amounts of heat energy as well as CO2. So the change in heat energy in this case is negative, and we call the change in heat energy a change in enthalpy. Enthalpy, I realize it's a similar word to entropy. They mean very different things. Entropy is disorder. Enthalpy is the heat of a reaction. The change in heat of the reaction is the change in enthalpy. We abbreviate it as delta H. And because it's going down in the chemical reaction, because it's being produced in the chemical reaction, the delta H is a negative value. We're not going to worry about the positive and negative, but I'm just telling you that in this case, the delta H is negative. The important thing to remember here is that heat is a product. It's being produced in this reaction. And you'll notice that in this energy diagram, I forgot to mention the reaction coordinate. This is just saying we're going from the things on the left to the things on the right. You can think of it as time, but the fact is it's not always an even flow of time. Some parts of the reaction may be very fast, some parts may be slow. So instead of calling it time, we call it reaction coordinate. And we talked about this a little bit when we were talking about kinetics in a previous module. So why does burning carbon to produce CO2, why is that exothermic? Well, initially we're breaking the bonds that hold oxygen gas together. And this is why we go through that high energy activation state. This is very unstable to break bonds apart like this. And the breaking of the bonds is the most unstable part. Once you're broken, it's slightly more stable, but these are both very unstable states. And then they combine together to form carbon dioxide. And now carbon forms 2 double bonds. One double bond to one oxygen and one double bond to the other oxygen. And both of these are very strong, very stable bonds. In fact, this is the reason why it's so hard to get rid of CO2. It's a very stable molecule. And because it's a more stable molecule, it means it's lower energy. So we're starting from high energy oxygen and medium energy carbon, and we're going to very low energy, very stable CO2 in the end. So we're going from high energy reactants to low energy products, and that energy has to go somewhere. So it's released as a result of making better bonds, making more stable bonds, and the energy is released, so we have an exothermic reaction. So let's talk about an endothermic reaction. Here's a reaction where calcium carbonate is in a decomposition reaction to produce calcium oxide plus carbon dioxide, CO2. And in this reaction, being endothermic, heat is going into the reaction. In other words, heat has to be added to the reactants to make the products. So that is telling us that the reactants are lower energy than the products. We only have one reactant, calcium carbonate, and this reactant requires added energy in order to produce the products. And again, I'm showing the transition state in green, but we're going to ignore that for just now. We're going to focus on the starting state of calcium carbonate and the final products of calcium oxide and CO2. And the products are more high energy. That is, they're more unstable than the starting material. So heat is absorbed in the reaction. You have to add heat to the calcium carbonate. It's absorbed by the calcium carbonate to produce the two products. In other words, the reactants are more stable, the products are less stable. And as a result, this means that heat energy is a reactant in this particular reaction. You have to add it on the left side of the equation. So because we're adding heat to the reaction, our change in enthalpy is positive, and in this case, it's a positive 176 kilojoules of energy for every 1 mole of calcium carbonate that we are decomposing. It is a positive change in enthalpy. So let's look at actual quantitative values of energy involved in a chemical reaction. So if we write a balanced equation that includes a change in enthalpy, in other words, the amount of heat the reaction produces or absorbed, we call that combined equation the thermochemical equation. It used to be the chemical equation. We're adding in the heat information, so we call it the thermochemical equation. And what this tells us is a mole ratio of the number of moles of each of the reactants and each of the products, and a ratio to the amount of energy. In other words, we have 1 mole of CH4, CH4 is methane, reacting with 2 moles of oxygen to produce 1 mole of carbon dioxide, 2 moles of H2O, plus 802.2 kilojoules of energy. Now you notice I don't bother writing the plus sign, the negative sign here, because I put it on the right side of the equation. By putting it on the right side of the equation as a product, it means that the change in heat, the change in enthalpy, was a negative value. But when we write it as a product, we don't need to show that negative sign. It is that much energy, 802.2 kilojoules of energy, is a product. It is released. So this is telling us that 1 mole of methane will generate, once it's combusted, it will generate 802.2 kilojoules of energy. But it also tells us all the other ratios to the other reactants and products in this thermochemical equation. When it says that when you generate 802.2 kilojoules of energy, you must have also produced 2 moles of water. You must have also produced 1 mole of carbon dioxide. You must have also used up 2 moles of oxygen gas. You must have also used up 1 mole of methane. So this allows you to make ratios of any 2 of these 5 components to the reaction. Just like we did with balanced equations in our stoichiometry calculations, we can now make ratios instead of 1 mole of methane to 2 moles of water. We can say 1 mole of methane to 802.2 kilojoules of heat or energy. So you can use the same convention to create conversion factors in stoichiometry when you're being asked to discuss heat related to a chemical reaction. So here's a problem. If 10.3 grams, so anytime you see grams in a problem, think that you probably have to turn it into moles. 10.3 grams of methane are burned completely. That means it completely is turned into carbon dioxide, water, and heat. Then how much heat will be produced? Well, first you're going to turn the 10.3 grams of methane into moles of methane, and you already know how to do that. And then once you have the moles of methane, You multiply it by a second conversion factor. You put moles of methane on the bottom. You put kilojoules on the top before you ever put any numbers in. And then you look at the thermochemical equation and you realize, oh, it's 802.2 kilojoules, and it's 1 mole of methane. And if we were dealing with water, I would have put 802.2 kilojoules per 2 moles of water, or per 2 moles of oxygen gas, if it was oxygen that I was starting with. Whatever you start with, it's going to be, you turn that into moles, and then it will be the amount of energy in the reaction per number of moles that are in that thermochemical equation, that balanced equation with heat energy added. And we see here that 10.3 grams of methane will result in 515 kilojoules of heat released. Does that make sense? Well, we know 1 mole of methane will produce 802.2 kilojoules of energy. And 1 mole of methane is about 16 grams, 12 grams for the carbon and 1 for each of the 4 hydrogens. We add those up, so the molar mass is about 16. In this case, you can see it's actually 16.0425 grams per mole. But it's about 16 grams. We're not starting with 16 grams. We're only starting with 10 grams. So we're not going to make the whole 802.2 kilojoules. We'll make a little bit less because we have a little bit less grams than enough for a whole mole. And 515 is a little bit less than 802.2. So this makes total sense. So the balanced equation tells you exactly how much heat is produced or released. I'm sorry, produced or released mean the same thing, or absorbed per chemical reaction that's written, per equation that you write. That could be a balanced equation. It could be a version of a balanced equation that doesn't have whole numbers in it. But you can write an equation and you can write an amount of heat that is associated with that reaction. So here's another reaction. We have 2 moles of C4H10. You learn the name as tetracarbon decahydride, but the proper organic chemistry name for this is butane, as in a butane lighter. And when you burn 2 moles of butane with 13 moles of oxygen, you'll produce 8 moles of carbon dioxide gas and 10 moles of water, but you'll also produce 5,755 kilojoules, that's 1,000 joules, of heat energy. In other words, it's 5,755,000 joules of energy. This is an enormous amount of heat that's generated from burning 2 moles of butane. This is why we burn fuels. They generate so much heat. So now we have a ratio. We know the ratio of any number of moles of any of the 4 substances with the energy produced, 5755 kilojoules. And this allows us to do all kinds of problems involving heat energy. So if I have, here, let's look at the first question. If you have 5.76 grams of butane and they're burned, how much heat is produced? And I've been kind enough to give you the molar mass. Make sure you calculate the same value. It's 4 carbons and 10 hydrogens. Does that make sense? Well, each carbon is about 12. 4 of those is 48. Each hydrogen is 1. 10 of those is 10. 48 and 10 is 58. So the number makes sense. So we do not have a whole mole. In fact, we have a little less than 1/10 of a mole, 5.76 grams instead of 58.1222 grams. So just looking at this equation, before I even do any math, I can see that I have about 1/10 of a mole of butane to start with, and I know that 2 whole moles will make the amount of energy shown in our thermochemical equation. So we're going to make much less energy than 5,755 kilojoules. So we're going to start with what we have. We always start with what we have. We turn our grams of butane into moles of butane by creating our classic conversion factor of grams on the bottom, moles on the top, and we use the molar mass to populate it with the numbers, 58.1222 grams. And 1 mole of butane are equivalent to one another. That's our first conversion factor. And then our second, in order to convert moles of butane, we put moles of butane in the bottom of our second conversion factor. We put kilojoules on the top. And then we look at our equation and see, oh, it's 5755 kilojoules. It's 2 moles of butane. We plug that in. We do our math with our calculator. And we see we get 258 kilojoules of heat released. This is a significant amount of heat, but obviously much, much less than the 5,755 that you would get with 2 whole moles of butane. Second question, if 45.7 grams of oxygen are consumed, how much heat is produced? And I give you the molar mass of oxygen. This is just 2 times the molar mass of each oxygen atom, 31.9988 grams per mole. We turn the grams into moles, and we know that 13 moles of oxygen will make 5755 kilojoules of energy. Remember, every time you make your conversion factor, put the units in first. Moles of oxygen on the bottom, kilojoules on top, then plug in the numbers from your equation. And then you see your value, 632 kilojoules of energy released. In our last problem, if 55.9 grams of carbon dioxide are produced. So you'll notice in the first question, we're talking about one of the reactants. In the second question, we're talking about one of the other reactant. And in the third question, we're talking about one of the products. It doesn't matter which one of the 4 we talk about. If we know how much was involved in the reaction, we can turn any one of those into any other of the 5 in this thermochemical equation. So now we're starting with CO2. We turn it into moles using its molar mass. And now we know that 8 moles of CO2 production is associated with 5755 kilojoules of energy being released. And we see that our initial 55.9 grams of carbon dioxide, if we got that much produced, we must have also produced 914 kilojoules of heat.